Today in section 1.5, we're going to talk about limits, specifically the limits of functions, but before I get to that, I want to talk about the limit of a sequence. So a sequence is just an ordered list of numbers. So here I have what we call the harmonic sequence, which is just 1 over 1, followed by 1 over 2, followed by 1 over 3, followed by 1 over 4, etc. And the idea is, what is the limit of this sequence? That is to say, what is this sequence getting close to? Now, I think we can all agree that this sequence is getting close to 0, right? Because as the bottom number gets bigger and bigger, we get to 1 over a million, 1 over a billion, 1 over a trillion. We get really, really small. We're getting really close to 0. Now, one thing to note is that nothing in this sequence here, nothing in this sequence will ever actually equal 0, but we will get incredibly, incredibly close. But a good question is what do we mean when we say when we get close? Because these numbers are all getting close to 0, but they're all also getting closer to -1, right? Because 1 over a trillion is closer to -1 than 1 over 2. But the idea is that we can get what we call arbitrarily close. That is to say, as close as we want. So if you want to get to within 1/1,000,000,000th of 0, all you have to do is go out far enough along in this sequence here, and eventually you'll find a number where all the numbers after that are within that range. So let me write that out. If you want to get within 1, whatever that is, 1/100,000th, all you have to do is go out far enough in this sequence here, oddly enough to the 100,000th number, and then you'll get to be within that range of 0. But you'll never get that close to -1. And so because of that, because we can get arbitrarily close to 0, we say that this sequence limits to 0. Another way of saying that is the limit of the sequence is 0. Okay, so we have a good intuitive understanding of the limit of a sequence, but what does this have to do with the limit of a function? Well, when we're calculating the limit of a function, all we do is we pick a sequence of x values, and we look at the corresponding sequence of y values, and we see if the y value is a limit to anything. So here, in this example, we have f of x equals x squared plus 1, and we're curious, what is this thing? And this thing reads the limit as x approaches 1 of f of x. So as our x values get closer and closer to 1, what does f of x get closer to? So one thing we can do is we can pick x values near 1. So here I have a chart here, and I picked x equals 0.9, x equals 0.99, 0.99, then I have a 1 here, 1.001, 1.01, 1.1, etc. And so these x values give us a corresponding f of x value on both sides of 1. And the question is, what do these f of x values get close to? So here, on the 0.9, 0.99 side of 1, we have the corresponding output values of 1.81, 1.9801, 1.998001, and as you can see, these values are getting close to the number 2. And similarly, on the side where we're bigger than 1, starting at 1.1, we have the output value 2.21. For 1.01, we have 2.0201. And for 1.001, we have 2.002001. And as you can see, these output values, they are all getting very close to the number 2. And so that tells us that the limit as x approaches 1 of f of x equals 2. All right, so again, just to reiterate, the idea is we're looking for what y value we are getting really close to as our x value gets really close to a certain value. So one way you can solve that is by making the tables like we did in the last example. The other quick and dirty way you can do it is to look at the graphs of the functions. So here we are asked to find the limit as x approaches 1 of f of x for the following functions. F of x equals x squared minus 1 over x minus 1. F of x equals the absolute value of x minus 1 over x minus 1. And lastly, f of x equals x if x does not equal 1, and 0 if x equals 1. So if we look at the graph of this first function here, if we zoom in, we see it looks something like this. It's a straight line with a hole at x equals 1. And we have that hole because if we plug in 1 into our function, we get a 0 on the denominator. But as you can see, as we get really close to 1 in our x values here, as we get really, really close, our y values here are going to get really, really close to where this hole is at y equals 2. So near x equals 1, our y values near y equals 2. They don't ever quite equal 2, but they get arbitrarily close. All right, let's take a zoom out. Zoom back in on this next function, absolute value of x minus 1 over x minus 1. Again here, our function is going to have a jump in it at x equals 1. But what's the limit of the output values? So as x gets really close to 1 this way, coming from the right-hand side, as x gets really close to 1 coming this way from the right-hand side, our output values all stay the same. To the right of 1, our output values are all 1. But to the left of 1, so over here, our output values are all negative 1. So if we're coming from one way, we're approaching at 1. If we're coming from the other way, we're approaching at negative 1. What are we approaching? Well, we're not really approaching anything. We're approaching two numbers at the same time, but we don't have a well-defined limit if we're approaching two numbers at the same time. So what do we do? What do we do if we're approaching two numbers? Well, what we do is we say the limit does not exist. Just like at the end of Mean Girls, the limit does not exist. All right, and our last function here, f of x equals x if x is not equal to 1, and 0 if x equals 1. So let's zoom in here. Again, we just have a straight line at y equals x with the added caveat that we have a hole in our line at x equals 1 and a little dot here at the point 1, 0. So in all actuality, the f of x value when x equals 1 is 0. But that does not mean that the limit is 0. Remember, the limit, we only care about what happens when we're close to a point. So when we're really close to x equals 0, what's happening? Well, when we're really close to x equals 0, if we're getting really, really close to x equals 0, our y values are getting really, really close to y equals 1. Again, they're never going to quite equal y equals 1, but they're going to get very, very, very close. And they're limiting into 1 from both sides, from the top and the bottom. So we say the limit is 1. All right. This brings us to our formal definition of the limit. So here's our definition. If f of x becomes arbitrarily close to a single number L as x approaches c from either side, then the limit as x approaches c of f of x equals L. So here c and L are just constants. They can change depending on whatever you want, depending on the function. But again, the output values of f of x have to become arbitrarily close to a single number L as x approaches our given number c from either side. And that tells us the limit as x approaches c of f of x equals L. And here's a note when it comes to calculating limits. Not so much in this chapter, because in this chapter you're going to have to work with a lot of weird limits and whatnot to fully understand the idea. But more often than not, especially later on, all you have to do to calculate a limit is to plug it in. That is to say, the limit as x approaches c of a function f of x equals f of c. Now this works for functions if the function is continuous, but we'll talk more about that later. But for example, if we want to calculate the limit as x approaches negative 2 of x to the fourth minus 1, well, all we need to do is plug in negative 2, and we get negative 2 to the fourth minus 1, which is 15. Again, this does not work in all cases, but it works more often than not. All right, and here are some basic rules for limits. And here b is any constant. The limit as x approaches c of b is b. That is to say, if we have a constant function like f of x equals 100, then no matter what limit we're working with, we're always going to be approaching 100. Here, the limit as x approaches c of f of x equals c. That is to say, if we just have f of x equals x, that kind of straight line that we all know and love, the output values will be getting close to x. Or sorry, the output values will be getting close to c. Just a couple more. The limit as x approaches c of x to the n equals c to the n. So that's one of those just plug it in kind of things. And then lastly, the limit as x approaches c of the nth root of x equals the nth root of c, with the caveat, if n is even, c must be positive, because otherwise you'd be taking the square root or the fourth root, etc. of a negative number, which can't happen. And let's see how this looks in practice. So for example, the limit as x approaches 9 of negative 3 equals negative 3. So here our function is a constant negative 3, so no matter what this number is, we're always approaching negative 3. Here we have the limit as x approaches 9 of x equals 9. You just plug in. The limit as x approaches 9 of x cubed equals 9 cubed, which is 729. Again, you just plug in. And then lastly, the limit as x approaches 9 of the square root of x equals the square root of 9 equals 3.